All right. So you see this live now and tell
Yeah,
me what to
that's it.
begin.
It's good.
Okay.
So it's my great pleasure to introduce the final speaker of today, Jimmy Copper, who has defended his thesis yesterday, right? So congratulations.
Well,
Yeah,
3 days ago, but
two
yes.
days ago, sorry. But very recently. Yeah, everyone's clapping. Well done. Welcome, doctor. And on to you.
Yes. Thank you very much for the intro. Hi. So hi, I'm Jimmy. And I'll be talking about some work I did with some colleagues in probabilistic programming, where in the process we discovered something that actually seems pretty important, a bit fundamental to higher order effects. So I was invited to come to this talk to bridge the two communities. Uh, so I defended my thesis so recently. I knew I would not be preparing a full 30-minute talk, so that's why I'm going last. So I can go under a bit. Should be a nice reprieve from the usual behavior of talks, and this is estimated about a 17 to 18-minute talk. So let's do it. Okay. Let's play a game. In this game, I'm going to roll a die, and then I want you to predict the die roll. We'll compare. If your prediction is within one of the actual die roll, then you win. Otherwise, you lose. Okay, you all have your predictions? Now say you played 2 and you lost. Given that information, how likely would you have been to win had you played 4? So how do we evaluate this? Well, we condition on 2 losing, so we know the die roll couldn't be a 1, 2, or 3. And we win if it's a 4 or 5, and lose if it's a 6, so 2/3. What we just performed there in solving that problem is a counterfactual inference. And the process we use is threefold. First, we look at the factual world, what happens. The 2 lost. We abduce what the rolls of the die could have been, 4, 5, or 6. We intervene, do an action on the states, change the guess retroactively to 4, and then predict the win-or-loss behavior in this counterfactual world. These kinds of counterfactual inference questions are very common and important in law and in policy. What would have happened had the patient been treated a few minutes earlier? What would have happened if this house was made of a slightly less flammable material when the spark caught? What would have happened had the US stayed in Afghanistan a little bit longer? These are questions we must answer frequently within life, and they have huge consequences. In our ICML paper, we created counterfactual inference as a language feature within a probabilistic programming language. So here's what the die game looks like. And I'm going to walk through this code in detail for a bit, so that I'm going to show you what exactly is special about it from an effects point of view. So here's the code in a version of our Omega language. So first F here, it just takes a random number, compares it to the guess X, returns win or lose. Next, we set the guess at 2 and Y to running the game on this guess. Okay, so what does this last guy do? So we're looking at the value of Y, whether win or lose, but conditioned in the counterfactual world where guess had been set to 4, where in the factual world, Y was observed to actually be a lose. And we sample and draw from here. So there are 3 things going on in this last part, effect-wise. This conditioning and sampling is an ordinary probabilistic programming language feature. We'll be talking briefly about this in a few minutes for those not familiar. This counterfactual intervention conditioning part is the subject of this talk. So I was called into this project primarily as the most hardcore PL guy to design the semantics. And so I designed the semantics of this counterfactual do operator, and I realized that it was a bit too simple. It must already exist, and it does. Today I'll be showing you how counterfactuals is a combination of laziness and dynamic scope. And as I was discussing with the anonymous reviewers for Hope, I think that there's a lot of ideas that you and the audience can run with from this. So I am going to strive this talk to give you a pretty strong operational understanding so that you might, with a little bit of looking stuff up, be able to run some counterfactual programs by hand. So I'm going to be going pretty slow in parts because I want you to understand none of these ideas are particularly complex, very simple in fact, but there are a couple layers to understand first. So, but I'm going to be pausing at points to give you time to digest things. So first, non-directly effect-related simple idea number one, let's talk about the basics of causality. So, what I'm about to show you is pretty much straight out of the Pearl School, especially his book. Not the only way people talk about causality, but it's a very computer science friendly one. Philosophically beautiful, lots of graphs. The object of study in this school of causal inference is the structural causal model, which I like to think of them as straight line programs, which they are. Here's a program. It rains, or doesn't, according to some thing. If there was no rain, then the sprinkler turns on. If there was rain, the sprinkler did not turn on. The grass is wet if either there was rain or a sprinkler. Okay? So let's execute that. So say it doesn't rain, the sprinkler comes on, and whoa, the grass is wet. Amazing. Now let's start to play with this model a bit. So what if we had turned the sprinkler off? So when I ask the question, what happens? Is the grass wet when there's no rain and no sprinkler? So look at this expression, like, okay, this makes perfect sense. How likely is it to be wet grass when there's no rain and no sprinkler? But that's not what this says, because conventional probability, this is only defined if you had observed a state in the wild with no rain and no sprinkler. And until we reached and turned the sprinkler off, there are no rain, no sprinkler states, so that condition is a giant division by zero, and this is actually undefined. If you just look at the data, this could be anything. But this makes perfect sense. So we're going to chop that rain to sprinkler edge. Whoosh, there it goes. We'll really get a different model, one in which we've basically aligned this program to setting sprinkler to false. And we can run this program as normal. Rain off, sprinkler off, grass is not wet. Wow. So we've already stepped outside the bounds of conventional probability theory, conventional statistics. Now we're looking at this funny expression, P of wet grass given not rain and dew, not sprinkler. That refers to the execution of this alternative intervening model. Here we can see the grass is clearly not wet when there's no rain and no sprinkler. That's intervention. And now we have the ingredients to think about counterfactuals. So let's ask the question, if the sprinkler had not come on, would the grass be dry? So here's how that works. You look at the factual world, you see, I told you, the grass was wet and the sprinkler did come on. These are the observed facts, we condition on them. From that, we can deduce that since the sprinkler turned on, it must not have rained. And so we're going to pull all the non-determinism out of the system. So we'll say whether rain was actually a deterministic cause of some other factors, call it clouds, call it God, what have you. These are further reduced. Now we know the backgrounds. We can start to look at the counterfactual world. In the counterfactual world, still does not rain. God makes the same decision, but we say, what if the sprinkler had not come on? So in this counterfactual world, we perform this intervention. And now we can deduce that, indeed, had the sprinkler not come on, the grass would be dry. And that is the abduction, intervention or action, and prediction. Those are the three steps of the counterfactual inference. So what we just computed was this weird quantity. P, the grass is wet, given sprinkler came on, comma, do, sprinkler doesn't come on. Conditioning on sprinkler and do not sprinkler. What is this? It means we observed that actually happens. We abduce other facts we can, and ask what happens had we intervened. So I'm going to pause on this slide for about 45 minutes. I think this is a pretty elegant idea, but sorry, I said 45 minutes. We'll pause here about 45 seconds just to let you stare at this sink in a bit, because we're going to be building on it soon. And if you think I already understand it, then just take a nice 30-second breather. Okay, let's resume. Oh, this is starting to sink in. If it's new, it's counterfactuals are often regarded as mysterious, but this is very beautiful semantics. So I'm going to introduce probabilistic programming. So here, even though I'm using these P's, everything 0, 1, it's deterministic. Let's make it non-deterministic. I'm going to introduce probabilistic programming just long enough to kind of brush it aside. So probabilistic programming, we think of the world has there are many possible worlds. Each of these possible worlds executes and their states evolve. But at certain points, something non-deterministic can happen. And it's like ordinary non-determinism, and the state branches. And the state branches again. But then, here's the rub. You can say, well, this current state seems pretty unlikely, or seems pretty likely. And when change the weights of the current states. In probabilistic programming, then the magic comes when we put this defectable computation in a box. We'd be God looking from the outside and saying, look at these final states. Sample from these worlds based on the likelihood. Give me probabilities, count them. And, oh, there's an entire field and conferences about how to do this without enumeration. I'm just going to bring this up. It's actually, even though counterfactuals kind of are usually thought as belonging in the world of statistics, probability, the counterfactual stuff I'm going to show you today is mostly orthogonal to this, but the application we know, when you see a twin network being built, just know that usually there is some conditioning and statistical inference involved. So now, let's bring counterfactuals into our programming languages. So we saw how to define a counterfactual for a straight line program by constructing this twin network. I have two copies of the model, one real, one which I modified a bit, but they share some background facts. So how do we extend this idea of a twin network to an arbitrary program? So let's look at this program again, and I'm going to split it up into a few parts, talk them independently. F is how the game works, can leave that aside. So we run this y given do of guess 0, 4. What we want to think of is that we are kind of dynamically a twin network. We're copying the previous state in the program. Basically, two copies of the execution, the factual and counterfactual executions. And
James?
Okay, I'm hearing a weird beep. Yeah?
Yeah. I think your screen is no longer sharing because something happened. Hello? Right. But can people hear me? Can someone say in the chat that they can hear me? Yeah, okay, that's great. So, yeah, we can wait a few minutes and
yeah, I think he might be rebooting his computer.
right. I mean, officially, this is the time the workshop is meant to finish. So I guess if people have pressing issues, they can wrap here. But I see, oh, James, let's see. No, he's disappeared.
Well, I think by the sound, it could be his computer out of charge. So
right. Well, we can take advantage of the time to thank the PC, for example, and all the participants. Yep, everyone is clapping. Thank you. Thanks all for making Hope happen this year. Hope hopefully will resume next year as well, right, Oleg?
yeah.
I would be in charge, but Oleg would be. And hopefully it will be approved. Hello, James.
Hello. Hi. Yes. So I just refreshed my browser a minute ago.
Fix it. You need to share your screen again if you.
Yes. So. Right now. Or do I need to go back?
I can't see your screen yet. Maybe turn off the video so that, because it says that your connection is not great. So if you turn off the video, maybe that. Oh, okay. Can you hear me?
Yeah. Yes, I hear you.
Okay.
So did you see everything up until the slide?
Yeah, we saw.
Okay, it's just go from here, right?
Yep. But maybe turn off your video just to make sure that the connection is more stable.
Okay, yeah. I'm doing so.
Thanks. So
all right. So I talked about how kind of dynamically creating this to a network, copying the previous computation. Now, once we copied everything that happened to this point.
Your screen sharing has disappeared.
Yeah, it's not great.
Probabilistic programming.
James, you just got completely cut off.
So this scales up pretty well. I think weird beeping again. I'm getting weird beeping. Okay. Every time that happens, little alarms, technical difficulties that I can't see when I'm presenting.
James, we can't see anything.
So we implemented this in a real probabilistic programming language called and it can have these counterfactuals, and it's pretty interesting programs. And you do things like for about data pedestrian, determine if like a single frame, because the speed caused the lower level semantics. Laziness plus dynamic scope equals counterfactuals. So, and by laziness, I actually need to call by name. We are not going to be memorizing computations, we'll be repeating computations many times, potentially. So let's look at these first few lines. Since this is lazy, of course, the let rule does nothing other than bind a closure. So guess gets balanced to closure empty state with value 2. And then y now have a state where it's bound to a closure where guess has been set as before. And when you want, and if you look at this var rule, it's only when you want to use this y are you going to evaluate after the guess. And you're going to do this, and at least in the semantics, every single time you reference y. It's call by name. Now let's add the dynamic scope, and I need a bit more space in my slides. So, okay, moving this around a bit. Right, so now let's look at this do part. Well, so here's the rule for do. And basically all the work is done in this retroactive update. Well, what does this retroactive update do? Well, because I've stored the full provenance of y, I've stored the closure, the computation that produced it, and then within that computation, I've stored things like guess, all the variables in there. I can basically just walk the state as a data structure and change yes to 4 everywhere. Bam, bam, yes is now 4. And now when I run y, it's giving me the value that would have been had guess been 4. So that is counterfactual work. So let's compare this briefly to the more classical dynamic scope delets operator. So look at this program on the left. I'm going to rebind p to 2 before running this function f. So I call it p is 2. Y had been set to p earlier though, so y is 1. And this gives me 3. On the right, I have basically the same program, but I'm using do instead of delet. This time, I rebound p to 2, but now when I click y, I'm getting the value that y would have been had p been 2. So, 4. So the classical delet is running commutation where I change a variable, whereas do is doing something cooler. It's running this computation with not only that variable rebounds, but kind of gone back in time and changed the provenance, that everything that is data dependent on this changed variable is also updated accordingly. So I've only found one person who's written before about the combination of laziness and dynamic scope, and he basically said it's really complicated, doesn't do what you want it to do, don't combine them. But what we've seen today is that actually laziness and dynamic scope combine beautifully. It's not useless, it's counterfactuals. All right, so hope you all had a great hope, and I'm here for questions.
Thanks. Yeah, there were a few times it got cut out during the last bit. So maybe if you could upload your slides to the webpage or link to the paper from the Hope webpage, then people would be very happy, because I had some personal requests for that. Yes, people are very happy about that. So I encourage you to upload your slides to the webpage so people can have another look at them afterwards to catch up on the stuff that they missed. Any questions? I can see there's a couple in the chat. Can you say more about why counterfactual inference?
Okay, so questions. Can I say more about why counterfactual inference is useful in programming? All the examples we have so far of counterfactual inference are from probabilistic modeling. So I showed you the example. I showed you the example of the question from a single frame deduce was the driver's speed caused the crash, and you do that basically by kind of having some variables for driver speed and a model for how fast it can brake and the reaction and whatnot. At the time they see the pedestrian, then you have a program that kind of renders a scene from that. You condition on the actual scene, and then you can ask a counterfactual question, have their speed been slower, would the pedestrian have not been hit? So that's the kind of questions we've been thinking about with counterfactual inference. For pure programming stuff outside of probabilistic modeling, there are probably uses for it, but we just haven't been thinking in that direction.
So your Tom asked you to show again one of the slides. Maybe he can tell us which one he means.
25 or 26 or 24.
Yeah, I just meant the slide you were just talking about. I think it's one that was cut off, or maybe I'm mistaken. But The slide with the car that you were just talking about. Which one was it?
Blah, blah, blah. Oof. Yes, here we are, 22.
Oh, okay. Yeah, this is when you come back in. Okay, thanks.
Okay. Okay, I suggest we take the rest of this to the social area, to the networking area. And thank Jimmy again. And congratulate him again. Thanks. Claps. And thank you everyone for persisting all the way through Hope. And thank you for making a Hope materialize this year, despite everything. Thanks. That's it. Okay, I'll stop the